Okay, let's talk about some interesting problems with gases. I want to talk about the stoichiometry of gases, but I want to start with learning how to calculate the density of gases and also the molar mass using our gas laws. Okay, so when we're talking about density, I just remind you that gases or anything that is less dense is going to float, and things that are more dense are going to sink. The way we calculate density is we take the mass and we divide by the volume. And if they have the same volume, if the volume is set, the one that has the lower mass is going to have the lower density. So this guy up here has a lower density. It's the one that's floating. Okay, let's take that density equation and figure out how we can figure out the density of gases by using our gas laws. So density is going to be mass over volume. And if we read this problem here, it says, what is the density of oxygen at STP? Now, we know that oxygen is oxygen gas, and we know that STP is 273.15 Kelvin, and we know that it is 1 atmosphere of pressure. So just that statement gives us a lot of information about the gas. But you might be thinking, to find density, we need to be able to find mass, and nowhere in the problem is mass given. So we're going to use a little trick. We're going to assume that we have an amount such as 1 mole. And when we reframe it like that, when we're looking at the density, we're looking at the mass of 1 mole divided by the volume of 1 mole. And that can help us kind of concentrate on where we're going to get these numbers. All right, so when we're trying to find the mass of 1 mole, that's pretty easy. We're just going to look at our periodic table, and we're going to figure out what the mass of oxygen gas is. Okay, so each oxygen weighs 16. So our mass is going to be 2 oxygen gases. That's 32 grams. That's the mass of 1 mole of oxygen gas. Okay, now I need to divide by the volume of 1 mole. So I'm trying to find the volume. I know the moles, and I also have this information over here. I have the temperature and the pressure. That means that I can use the ideal gas law. I'm trying to find the volume of 1 mole, so I'm going to rearrange this. And now I can put in my numbers. I'm working with 1 mole. R is a constant. I have my temperature. And my pressure is 1 atmosphere. Okay. And so my volume is 22.4 liters. That might be a number that you recognize. That is the volume of any gas if you have 1 mole at STP. But that is my volume here down at the bottom. And when you put that into your calculator, you should get 1.428. I'm thinking probably have 4 sig figs there. So it's actually 485. And rounded to 4 places, or 4 sig figs. So this would be 1.428, and the units are grams per liter. I'm going to clean this up just a little bit. And I want to, now that we've done that problem kind of the longish way, I want to go back to where we just had the mass and we were trying to find the volume. Okay, so we were here and we had just found the mass of 1 mole, and now we were trying to find the volume of 1 mole at STP. Now, if at this point you had realized that this was a number that you might know, 22.4 liters, we wouldn't have had to do all the work that was down here. We could have just put in the 22.4 liters here, and we could have done that work. So knowing that 1 mole of any gas occupies 22.4 liters at STP is really useful when you're doing density calculations and you're assuming that you have 1 mole. Okay, let's try and do another kind of similar problem. In this problem, we are going to be calculating the molar mass, and molar mass is in units of grams per mole. Sometimes we like to write it like this. Okay. And here we're going to do the same kind of thing as we did with our density. We're going to assume that we have a certain amount. We will find the grams of that certain amount, and we will use the ideal gas law to find the moles. Let's see how we can apply that to this problem. Okay, we're going to kind of read as we go along and figure out what we have. All right, so it says the gas has a density of this, and I'm just going to write that off to the side, 3.57 grams per 1 liter. It's at 2 atmospheres and 300 K. What is the molar weight of the gas? So I'm looking for molar mass. I'm looking for grams divided by moles. All right, let's see how we can work this problem out. I'm going to concentrate on my units that I want here, my grams and my moles, and figure out where I can get those from the information given in the problem. I said that we could use the same trick as we did with density, where we assume that we have a certain amount. And I'm going to concentrate on this density here. It says that if we have 1 liter, we know the mass, 3.57 grams. So if I put the 3.57 grams here, I'm putting in the grams of 1 liter. On the bottom, I just need to find out the moles of 1 liter of this gas. So I'm going to do my work for that down here. So I already have the mass part, I have the grams part. I'm working on the moles part. I'm trying to find moles, and the information that I have is that I'm assuming that I have 1 liter, I have 2.00 atmospheres, and I have 300 Kelvin. So what I have there is I have moles, volume, pressure, and temperature. It looks like I can use the ideal gas law to take this information and convert to moles. So I'm going to write my ideal gas law. I'm going to divide both sides by RT, and I get PV over RT equals N, because those guys cancel out. Okay, putting in my numbers, my pressure is 2 atmospheres, my volume was 1 liter, and I'm assuming 1 liter, so that's really 1 liter to like an infinite number of sig figs. I know that I'm only writing it to 1 there, that's a little uncomfortable for me. Okay, R is 0.08206, and temperature is 300 Kelvin. All right, so on my calculator, I got 0.08124, and my units are moles. Okay, so that's how many moles 1 liter of this gas is going to take up. And now I can put that right into here. Okay, so I'm actually going to do that. I'm going to put in my moles here. And when I put that into my calculator, I get 43.94, should be to 3 sig figs, grams per mole. All right, so what we did is we were able to calculate the molar mass by assuming that we had 1 liter, and then using the molar mass equation, grams per mole, we would know the grams. We used the ideal gas law to find the moles, and we found that it weighs about 44 grams per mole. Now this problem down here, assuming the gas is a pure element, what is the gas? What we would normally do is we would just go to the periodic table and we would see what weighs 44 grams per mole. But I'm just realizing that I had changed this problem so that the numbers are a little bit different. It doesn't actually match any element that would be a gas. It would be a metal. I'm looking at my periodic table. The one that matches the most close, 44, would be like ruthenium. Ruthenium's not going to be a gas at 300 Kelvin. That's not really possible. So anyways, I just remembered that I had changed this problem and I knew it wasn't gonna match a pure element anymore. So we're not gonna answer that part. What I do want to do is I want us to do some stoichiometry with some moles and things like that. And I just want to review stoichiometry for a few minutes, just to get our minds back into kind of the swing of things. Okay, so this problem says how many grams of magnesium carbonate are needed to produce so many grams of carbon dioxide, and you're given a balanced chemical equation here. This is what we know to be a typical mass-to-mass problem. And if you can remember back to mass problems, you start with a mass, and here we're going to start with our 23.0 grams of carbon dioxide, and we end in a mass. We're trying to get to grams of magnesium carbonate. Mass-to-mass problems have the same steps each time. The first time you use a molar mass to convert to moles. So carbon dioxide is 44.01 grams per 1 mole. Then we use a mass-to-mass or a mole-to-mole ratio. I can see from my problems they are in a 1-to-1 ratio. All right, and then to convert moles of carbon dioxide to grams of carbon dioxide, I'm going to use the molar mass. And when I add that up, a magnesium, a carbon, and 3 oxygens is 84.32 grams. On my calculator, I got 44.06 grams per mole, just grams of magnesium carbonate. And so I was calculating a mass. I started with a mass. This is our typical mass-to-mass problem. And we use molar mass, and we use mole-to-mole ratios to make that happen. All right, one more practice before we kind of add gases to this. Here is a problem where it talks about the decomposition of potassium chlorate. It says how many grams of oxygen gas, we're trying to get to grams of oxygen gas, can be prepared from 4.5 grams KClO3. Okay. So we're going to first use the molar mass. For KClO3, it's 122.55 grams per 1 mole. And, I was just about to go on to my mole-to-mole ratio, and I was looking up here at the balanced chemical reaction, and I realized that it's not balanced. So let's do that. Let's see, I have 3 oxygens on this side, so I need to do 6 on this side. So that would mean a 2 here and a 2 there. Okay, so now I can use those coefficients. There are 2 moles KClO3 for every 3 moles O2. And then 1 mole of O2 is 32 grams. So that's my molar mass of oxygen. Okay, my answer was this. It should have 3 sig figs, so 1.76 grams of O2. So before we go on to gases, I just kind of want to reflect on this problem here. As we're going along and doing our mass-to-mass problem, when we did this step here, we went from grams of KClO3 to moles. of KClO3. And then we did this step here, and we got to moles of O2. Now that we know about the gas laws, oxygen gas is a gas, and once we get to moles, if we're given pressure, volume, and we always know R, we could calculate the temperature. Or if we were given pressure, we always know R, and volume, and temperature, we could calculate the volume. So in our calculations when we're doing with gases, we're going to see some calculations that are very similar up until this point. But then after this, once we get to moles of the gas, we're going to need to use some gas laws if we want to find the other variables like pressure, volume, or temperature. Okay, here's a problem that has to do with gases and stoichiometry. I'm going to read the problem, and I'm going to kind of label our variables here, maybe use this balanced chemical equation to help organize things a little bit. A sample of magnesium carbonate was heated, and the carbon dioxide is collected in a 10-liter flask. So that means we know that a gas always expands to take up its entire container. So if it says that it's in a 10-liter container, that means I have 10 liters of my carbon dioxide gas. It was at a pressure of 755 torr and 20 degrees C. And then it says how many grams of magnesium carbonate were in the sample. So what I'm trying to find over here is grams. Okay. All right, we know how to take a volume, a pressure, and a temperature, and we know how to take that information and find moles. That's the ideal gas law. Once we find moles of carbon dioxide, we can find moles of magnesium carbonate, and once we find moles of magnesium carbonate, we can find grams of magnesium carbonate by using the molar mass. So I'm going to do my problem in that order. I'm first going to use the ideal gas law, PV equals nRT, to find moles, and then I'm going to do the stoichiometry group over here. I'm trying to find moles of my carbon dioxide gas. I'm going to rearrange my equation so that I get everything else on the other side. My pressure, guys, every time we use the ideal gas law, we know that the pressure has to be in atmospheres, the temperature has to be in Kelvin. So let's do those conversions first before we put them into the ideal gas law. When I converted my pressure to atmospheres, I got 0.9934 atmospheres to 3 sig figs, and my temperature, 273.15 added to 20 degrees is 293.15. Okay, so now I feel like I can actually put my things into PV equals nRT and I'll have the right units. All right, again, I was solving for N, that's PV over RT. So I'm going to put my pressure in, and I'll write that over to the side here. My pressure was the 0.9934. My volume is 10 liters. R is a constant. And my temperature was 293.15 Kelvin. My answer for moles of oxygen gas was 0.4129 to 3 sig figs. Okay. And so I basically have gotten myself to this point. Now it's just stoichiometry to get to grams. To get between moles and moles, you're going to use the mole-to-mole ratio. Between moles and grams, you're going to use the molar mass. I'm going to start that calculation over here. So I'm starting with my 4.129 moles O2. They are in a, I labeled it as O2, sorry, but it is CO2. Okay, so sorry about that. And they are in a 1-to-1 ratio. And then, so now I've gotten myself to this point, and now I need to get to the grams by using the molar mass. The mass was on a previous slide. It was one of our review stoichiometry problems had it. Grams, like this. So that's a magnesium, a carbon, and 3 oxygens. And my answer was 34.81636 figs. So I would just round it there. And that is grams of magnesium carbonate. Okay, so in this problem, we were able to use pressure, volume, and temperature to find moles of a gas, and then use stoichiometry to get to moles of a compound, and then we used molar mass to get to grams of that compound. All right, let's do one more practice problem. We have our balanced chemical equation here, and it says how many liters of carbon dioxide gas, so I'm going to be looking for liters, are produced from 0.5 liters of oxygen gas at STP. Now we know that STP stands for standard temperature and pressure, which is 1 atmosphere and 273.15 K. And if we did things like we did in the last problem, what we would do is we would take our volume, our pressure, and our temperature. We would use that information to find moles. Then we would find moles of carbon dioxide, and then we could find liters of carbon dioxide by knowing, again, that it was at STP. So we would have, when we say that it's at STP, we would also know the volume, not the volume, but we would know the temperature and the pressure on this side. But again, I want to remind us that this is at STP, and we know something about gases at STP. We know that 1 mole of gas at STP takes up 22.4 liters. And so that's going to be really helpful for us. It's going to be a big shortcut to do this problem. We can use this shortcut because both of the things we're working with, the oxygen gas and the carbon gas, are gases, so we can use this shortcut. And we can use it because we are at STP. So let's use that shortcut to our advantage. What I'm going to do is I'm going to start with my 0.5 liters of oxygen gas, and because we're at STP, I can say that 22.4 liters is 1 mole of O2. Then I can use a mole to mole ratio. They are in a 1:1 mole ratio. And then I can say 1 mole of CO2 will make 22.4 liters. Okay. So liters of oxygen gas cancels out with liters of oxygen gas, moles with moles, moles with moles, and I get liters of carbon dioxide. And when you do the math on your calculator, you're going to get 0.5 liters of carbon dioxide. I know the math wasn't super interesting there, but I wanted to set this up in a slightly different way, just so we can see how useful standard temperature and pressure shortcuts are. Okay, in this video, we started by talking about how to calculate the density of gases. We also talked about how to calculate the molar mass of gases. So those are some calculations. We also talked about just stoichiometry, a little review. And then we learned how to do stoichiometry calculations with gases. If you'd like some practice problems in your course pack, in the Gas Laws Practice 3, which I believe is on page 49. The problems would be number 1, 2, 3, and 6. There are also some problems on page 45, number 8, and page 47, number 7 and 8. So all those would be good practice problems to cover the material on this video.